Hi everybody, this is Gigi from Kauai Community College. This is a video on theorems that are relating to the concept of continuity. So the first one we would expect is if f and g are continuous, then the composite of these combinations of these functions are also continuous, right? And then the last one is pretty nice. If g is continuous at a point B and the limit of f of x as x go to c is b, then we will be able to evaluate this limit. Okay, now I want to demonstrate what the last one is here. When looking at something as complicated as this, how do we decipher this theorem? So g is the function cosine of x. G is continuous. We know the function cosine is continuous, right? And then we need to justify that the limit as x goes to pi over 2 of 2x plus sine of 3 pi over 2 plus x is equal to some value b. Okay, so let's go ahead and take the limit, and we know here when we're taking the limit we can just do a direct substitution here, because this is 2 times pi over 2 plus sine of 3 pi over 2 plus pi over 2. This right here is 0 because that would be sine of 4 pi over 2, which is 2 pi, and sine of 2 pi is 0. Plus this right here is going to be pi, so this value is pi, right? So then the theorem will say that that limit right there is going to equal to cosine of the limit of x goes to pi over 2 of this thing here, 2x plus sine of 3 pi over 2 plus x, which is cosine of, we just show, pi. And that is the g of b, right? G of pi. And cosine of pi is going to be -1. So, I mean, you can just say, well, can you just do a direct substitution and plug them all in and get that? And the answer is yes, that's essentially what you're doing. But what allows you to do that are these properties here. Okay, so these properties that has to do with a continuous function. So continuous function, you'll have things that you would expect to be continuous, like, you know, the sum, the quotient, the product, as long as the denominator of the quotient is not 0, and then you can take limit and you can just plug in the points as you see here. All right. Now, one really famous theorem that has to do with continuity is the intermediate value theorem, and it's very useful because we can use it to solve equations. So what does the IVM, which is the intermediate value theorem, what does the IVM say? If you have a function f of x that is continuous on a closed interval, then it will take on every value between f of a and f of b. In other words, this is what it's saying. If you have a function f of x that is continuous, and you have a point A, say right here, and say f of a is right here, right? And then you have a point B, say right there, and f of b is right there. Okay, now, so continuous function, and we have a closed interval A to B. Okay, now, if there was a u somewhere in between, so here's u is in between f of a and f of b. Here's u. what does this theorem guarantee for you to have? It guarantees for you to have at least, okay? So there is at least one value C in between A and B, where f of C, there is at least one value C, where f of C will have to equal to U. Okay, so that's what it means by the function will take on every value in between A and B. And honestly, if you have an A or a B up there and f is continuous, and when it's continuous, you have to draw without lifting your pencil. So yeah, you're going to cross that point C where f of C is equal to U, right? So how is this useful? It's useful in the fact that we could use the theorem to justify equation like this having a solution. Because sometimes if you know that it doesn't have a solution, then you don't have to go proceed to solve it, right? And you solve if you are expecting a solution. So we can use the intermediate value theorem to show that there is at least a solution. So again, f of x, and in this case, f of x is this part right here, and 4 is going to be our u. So our job is to, number one, justify that the function f of x is continuous, and number two, justify that u, which is 4, is in between some f of a and f of b. So our job is to come up with an a and a b. How do you come up with an a and b? Use your number sets, right? An a is the lower limit below 4, where f of a is below 4, and then the b is the higher limit where f of b is above 4, because u, which is 4, has to be in between f of a and f of b. So using my number sense, I would say, hey, look, let's a be 0 and b be 9. So f of a, put in 0, you have 0 plus square root of 1, which is 1. And f of 9 would be square root of 9, which is 3 plus square root of 10, which is roughly 6.16. So now that would be my upper and my lower limit. Well, let's justify that f of x is continuous. We know that square root of x is a continuous function within its domain from 0 to infinity. And then we also know that the square root of 1 plus x is continuous on its domain from -1 to infinity. Therefore, when I added them together to get f of x, our function f of x is continuous on the smaller domain, 0 to infinity. Okay, so f of x is continuous, and we have an a and a b where u is in between f of 1 and f of 9. So the intermediate value theorem will tell us then that there must be a c. There must be a c in between 1 and 9 for which f of c is equal to 4. Right? So then the given equation that we have will have at least one solution between 1 and 9. Now, what is the solution? The theorem doesn't tell you that. However, it will tell you that there is a solution, and the solution is somewhere between 1 and 9. Okay, that's what the intermediate value theorem says. Now, another theorem that ties differentiability and continuity is this, is that if a function is differentiable at point A, then it must be continuous at that point. Okay, now in Calculus 1, you don't really use this a lot, but it's something good to know for later, right? So the ones that is very useful is well, let's just talk about these types of if-then statement. when you have a conditional statement, there's variations of that, right? So if that's the if-then statement, then the inverse of that statement is if a function is not differentiable, then it's not continuous. Well, if you had taken logic or have seen logically equivalent statements, we know the inverse is not equivalent to that theorem, that if-then statement. So it's not true. If the function is not differentiable, then it's not continuous. Now, the other one that we always make a mistake of using is when you switch the order. If the function is continuous, then it's differentiable. And we know that the converse is not equivalent to the original function. Okay, so an example of that is the absolute value graph. The absolute value graph looks like this, right? Right here, not differentiable. However, it's continuous. There's my example right there. Or here, continuous, but what? Definitely not differentiable. Okay, so one counterexample for both of those statements. Now, so what is the one statement that is equivalent to our theorem? Mathematically equivalent to our theorem is a contrapositive. And the contrapositive is very useful. The contrapositive said if the function is not continuous, then it is not differentiable. Because sometimes it's easier just to prove a function is continuous or not than to prove that it's differentiable, right? Not differentiable. So the converse and the inverse are not the same. However, the contrapositive is logically equivalent. So you can say that these right here are logically equivalent. So we can use this theorem, or we can use the contrapositive of that theorem. And basically say differentiability implies continuity. And if it's not continuous, then it's definitely not differentiable. Any other variation of that is not true. And that is it.